Hello, welcome to the Mind Bits. On this channel, you will find courses related to embedded system development. My name is Bhupendrajit Singh. I'm working in embedded system development from a decade now. In this video, I'm going to teach you a very important skill called a board BringUp. You may have seen this term in job posting many times, and today you are going to learn about it. Next is the requirements. You should have Toolchain setup done on your computer. If not, you can watch previous video to do so. I will put a link in the description. You should be able to compile the code which is done in last video as well. Upload and monitor. You should have an ESP board and make sure you are able to upload the code and monitor the logs as well. So you will learn board bring up ESP32 startup flow. What happens before your main function get called? From my experience, I have listed few worth to know concepts. You will see them in a minute. I will be building a project in this video as well, which will be a Wi-Fi example project. Let's start with board bring up. The first thing is to inspect the hardware. You need to make sure the hardware is working and functional. So usually the hardware inspection is done by hardware designer, but during development you may need to troubleshoot hardware. Before you can start writing software, you need to make sure each peripheral is responding. So you should have knowledge to use multimeter, oscilloscope, power supply and function generator to verify your hardware. Next is the firmware integration and initialization. First, you need to develop a simple test version of the firmware and make sure all the available peripherals and devices are able to communicate. Let's take example if you have a sensor and you want to develop a software for that. We need to confirm if we are able to communicate with that particular sensor. Simple check would be initialize the required communication and read the ID of the sensor and confirm from the datasheet. The communication sometimes is a challenging part. You need to provide a proper ID if your sensor is based on I2C communication channels. Next, we need to work on the peripheral integration part and testing part as well. For example, you have tested one chip. Most of the project you are going to have multiple chips on a single board. So you have to have functions for each peripheral so that you can talk to them individually, making sure you are able to just say yes, those all peripherals are responding, and maybe you can print on the debug console where you can just list how many peripherals you have and if all of them are responding. You also need to build a debugging setup as well, so make sure you are able to debug your code. It could be either using a debugger such as a JTAG or something, or just printing logs on the console. So you should have a connection with your PC. ESP32 board, all of them usually have that USB connector which can be used for debugging as well. Why board bring up is important? You might think that why we need to put extra step in the development timeline. Well, when you are working on a complex project, you have to divide your project into milestones and divide the work across the team as well. And then you need to report back to the project manager as well. So timeline is important. Companies have to meet the deadlines to stay in the business. So you can have a short-term goal instead of just focusing on a final version of the firmware. So you can put that way as well. This also helps to have a kind of checklist. Okay, hardware is working, the test firmware is ready, and the hardware is tested. So this is important when you are working on a complex project in a bigger team. And it gives you a peace of mind during project development's life cycle. This is very important. We struggle a lot sometime when we don't know the problem. So is it a hardware giving us a issue or is it a firmware? So during development, if you are stuck, which happens normally, the reasons could be like, yes, it was working just this morning and now it is not. So what you can do in that case, you can load your test firmware to ensure that all the peripherals are still working and passing the test. If the test is passing, then debug your application. Or if it is not, then troubleshoot your hardware. Something is gone wrong. So this gives us a direction. So which way we need to troubleshoot. Let's understand in details. Here we have a circuit which is very common, like when you are working on any projects. You have a CPU and you have a sensor, And then how you are connecting this sensor is like maybe UART or SPI or I2C. So you need to figure out how many sensors you have, how we are communicating with them. And then you probably gonna have buttons. So you need to find out either are we polling the input or are we adding an interrupt, how we gonna debounce. These are the things you will be looking during this board bring up phase. You're gonna have LEDs, so which signal you are going to provide to turn the LED on or off. So that is hardware dependent and you need to figure it out. You also need to check the hardware schematic to find out if the outputs are pulled up or pulled down. If you have any motor, you need to see which type of motor it is, stepper motor, servo motor, DC or AC. And if you have any analog signal input, you need to know the reference voltage and maximum voltage to convert it. And the next step would be finding out the memory of the CPU and the flash storage of the CPU and also the clock frequency, and make sure clock is properly initialized. So these steps are normally nowadays are done by vendor. You have example codes to do that, and some vendors such as ST and Microchip, they provide some code configuration tool. You can do these all settings using graphical interface, which is very easy nowadays. You need to figure out the clock is internal or external, which clock you are using. If you are using internal clock, that is fine. If you are using external clock, you need to make sure your hardware have external crystal attached to right pins. So these are the details you will be confirming during the board bring up phase, making sure you go through the schematic and verify all these and have a notes of them so that you can write initial drivers. For example, if you are pressing a button, you should turn on the LED. If you are pressing again, you should turn off it. Motor, just start it. For example, same if you are pressing button for long period, then motor should start. If you are pressing button for 3 seconds, the motor should stop. Or you can control the motor with the potentiometer. Maybe if the potentiometer is all turned high, the motor should be running at high speed, and turned back to low, then the motor should be running at lower speed. Sensors, as we previously discussed, you should be able to read the IDs. Not all the sensors are going to have ID, but you find the ID on most of the sensor chips as well. But you can hook up some oscilloscope or a debugger to find out if your sensor is working or not. Let's look at the core of the ESP32. So ESP32 is extends 32-bit microprocessor based controller. So this processor is inside this big chip. So that's why we call it a controller, because the difference between controller and processor is only a processing unit. Controller have all the additional chips inside, like for example SPI driver, I2C, and all these UART, Ethernet, PWM, and the ADC timers as well. The RTC block is there, and other additional like Wi-Fi and Bluetooth. These all are hardware chips inside this block. That's why we call it a controller. This include like Wi-Fi, Bluetooth hardware, and then this is the radio frequency circuit, and this is the security part where you can run your cryptographic operations in hardware. And this processor usually comes with the dual core, and there are some versions having only one core on it. And the RTC does have a ULP coprocessor, so which is very rarely used. But when you are developing a lot of power efficient device, then you probably need to do some operation with the ULP processor. So it's ultra low power coprocessor, so where you can actually turn everything off if you don't need anything, and this will be the main guy looking after. And we have a flash and PSRAM, so it depends on each module. Some module have 4 megabits of flash, goes up to 16 megabits, and then some board does have a PSRAM, so which is external RAM, and these all are in the data sheet and you can read more. Have you ever wondered what happened before the main function get called? Basically, it's a startup sequence before the main function get called. So it's like first stage bootloader. So loads the second stage bootloader. So normally this happens pretty fast, so you don't notice. It start with the first stage bootloader. So no customization in this bootloader possible. This bootloader is already in your chip. And the second stage bootloader, which loads our application, this can be customized. Usually we load this bootloader along with our application as well. And then there are normally two ways to go, is a single application or the dual application. So in single application, only one application at a time present in the memory. We do this management by using the partition table. And the dual application, where over the air update is possible. So what's the main difference? In this, you won't be able to do the over the air update, but in this case you would be able to do the over the air update as well. But what will be happening, one application will be running and another application will be downloaded and placed into a dedicated place in the memory, and that is going to defined by the partition table. So we should know how we can change the partition table as well. So I will just put a reference in the description to read further in details. So next is worth to spend time on the concept. So I have a list of the concepts here. So memory model, basically these are the items you need to understand about the ESP32. So when you know about the memories, you would be able to identify maximum size of your application. If your application is way bigger, you want to have a OTA, then probably 4 megabits flash is not an option to go. If you have application more than 2 megabits, so how you can have two copies of each, because you need a memory for other stuff as well. There are options like have a bigger memory chips so that you can have a bigger applications. So usually ESP32 have a RAM and ROM, which is like internal RAM and ROM, and then there's external RAM, which is known as a PSRAM, and external flash as well. Next is the application startup flow, as we have seen in the previous slide. So we should know about the bootloader, partition table, and the application. I will be putting some links for the documentation as well in the description. We are using FreeRTOS on ESP32 because usually ESP32 runs complex applications. Even those applications seems not complex, but you are running a Bluetooth or Wi-Fi, those are already a complex task for a processor or controller. So FreeRTOS help us to manage that. If you have other peripherals such as like LCD or graphical display, so FreeRTOS help us to manage complex projects. So what you need to understand, the event scheduler, how the FreeRTOS is scheduling our task, and then how you can create tasks, and how you can use mutex and semaphore and queues to build a complex application where you can manage the complexity and keep the inter-process synchronization aligned. So let's build the Wi-Fi example project now. To start the Wi-Fi project, I just opened the VS Code, and we need to go to command palette and ESP-IDF welcome. And you can go to examples and you can find here Wi-Fi. So we will go with the station example here. So there are two modes. One is the station mode and one is the access point. In station mode, you can connect your ESP device to your home network, such as your router. But in access mode is opposite. You can connect other devices to your ESP. So today we will be focusing on station example. So create a example project. So as my example project is opened, I will just click outside and I will close all these pop-ups. This is the example code. So you can simply go to this icon and click on it. Sometime it takes a little longer. Okay. So we need to look at the example configuration here, and we need to enter the SSID and password and click on save. So when it is saved, you can close it. Here's the build icon down in this bottom toolbar. Click on that. Okay, so this project compiled with no error. You can see there are a lot of these red lines here. So I found a way to fix this, and you just need to paste this line in this folder under the C cpp properties.json. I will put this in the description. Now you can see your code is clean and there's no any warning. Now I'm gonna load this code on my ESP board. I'm using ESP rover kit. Click on the bigger number. If you have a rover kit, you are going to see two ports. If you have other ports, you would be seeing only one. In my case, I will select the COM5. So now COM5 is configured for this project, and I can simply click on the flash method and select the UART and then click on flash device. So you're actually writing the code on my ESP32 board. Okay, the flash is done. We can click on monitor. So now you can see the debug logs. So this main application is returned. You can see connected to this classic guest network, and then application main is returned. And you can see there are a lot of debug logs. So before main, there are like, bootloader stage 1, stage 2. So these logs are coming from those as well. You can see, and when those are done, the application is loaded. So loaded the application from partition, and then the what frequency we are running, and then the project details, and then the memory details here, starting the scheduler, the FreeRTOS scheduler, and then calling the main app. So if you go to main app, you can see we are initializing the storage, and we are going into this function. And in this function, we are initializing the Wi-Fi, and we are setting some events as well to look for. And we don't have any infinite loop, that's why we are returning back. So we will dig deep into this more in detail in the upcoming videos. So in the upcoming videos, we are going to talk about FreeRTOS. And next project we will be doing is the non-volatile storage, how we can store some configuration on your ESP32 and how you can read those configuration back from the memory. Thank you so much for watching this video. And if you are getting any value, please provide your feedback through comments. You can also put your comment if you need any other concept to be discussed. And stay tuned, and I will be making more videos in this series so that you can learn skills for your either next job or your next project. Thank you. See you again.